Hello, everyone. My name is Julian Amyapara,
My name is Muhammad Alwan.
My name is Nia Hamilton.
and today we're going to be talking about our Thermo 2 project.
Introduction. We were asked to determine the residual properties from the PVT data for refrigerant gas. We were given alpha, and the provided information is that the temperature of interest is 20 degrees Celsius, the TC and PC are 72 degrees Celsius and 5 MPa, and we're also given a molar mass of 73 kilograms per kilomoles. Objective. The tasks we were asked to complete are: 1. Create a chart that represents the behavior of compressibility factor Z with respect to reduced pressure. 2. Create a chart that shows the behavior of V residual. 3. Estimate the values for all residual properties, volume, Gibbs, enthalpy, and entropy. And 4. Present the results in a letter report. There were 6 main objectives that were used to be able to complete the task. 1. Gathering data for alpha gas with respect to our temperatures of interest. 2. Obtain values that represented the ideal gas with respect to the molar mass and the pressure that were taken from the temperature range that was selected. 3. Obtain the Z compressible factor. 4. Pressure reduction. 5. Graphs for the behavior of the ideal volume and residual volume from the actual gas and Z compressible factor with pressure reduction. And 6. Obtain values for the remaining residual for enthalpy, entropy, and Gibbs.
So first, to gather our data for the alpha gas for our temperature of interest, which was 20 degrees Celsius, we gathered the data with our chosen range of temperature between our temperature of interest. So our temperature interest, which was 20, as I said earlier, and we decided to choose a range between 0 degrees Celsius to 200 degrees Celsius, which is shown at this table 1. As you can see here, our temperatures in Celsius and converted them to Kelvin with our pressures of 50, 100, 150, 200, 300, and so on. So this table here is actually showing us our actual data for specific volume. So further on to that, continuing, we obtained these values, which represents the ideal gas for our molar mass, and the pressures, which was taken from our temperature ranges, which were selected. So from there, we use the equation of state of ideal gas law, which is PV equals RT, to find the volume. Then we use that, providing with our molar mass of 73 kilogram per kilomole, which is given to find our ideal gas volume, with the following table shown at 2. So over here, you can tell our ideal gas volume data at different temperatures and pressures. So as here, we have our pressures and our ideal gas data volume with our kilogram temperatures, Kelvin temperature.
Here we have to obtain the Z compressible factor. So the Z compressible factor is directly proportional to the specific volume values from the actual gas and indirectly proportional to specific volume values from the ideal gas, which allows you to use the equation here, the V actual over the V ideal. The table below shows the values here. It shows here from, again, 0 to 200 degrees Celsius. And here we have the pressure reduction. We calculate the reduced pressure by a relationship between reduced pressure and at a critical point of 5 megapascals that was given. And also here we use the reduced pressure equation, pressure reference over the pressure critical point. And below is the table for the reduced pressure.
Graphs for the behavior of the ideal volume and residual volume from the actual gas and Z compressible factor with pressure reduction. We first created the graph of the compressibility factor Z versus reduced pressure. We saw that as the actual gas started to increase along the pressure reduce, the further the actual gas moved from the ideal gas with respect to the compressible factor Z, which for the ideal gas is 1. And our graph is shown below of the compressible factor Z versus reduced pressure. Then we plotted residual volume versus temperature. We were able to determine that as the temperature increased with constant pressure, all the actual gas volume started to diverge from a linear slope, which is expected for an ideal gas with a constant pressure and increase in the temperature. And below is shown the residual volume versus temperature at various pressures.
So the sixth step was to obtain values from the remaining residual for enthalpy, entropy, and Gibbs energy. To obtain the values for the Z vector along with the residual properties state formulas. So in order for us to calculate, we started with our Gibbs residual. To find the Gibbs residual, we know that GR equals G subtracting G ideal. So in order to do that, we couldn't specifically use that equation. So we ended up having to take the integral of the Gibbs free energy over the RT. So we took the integral Z factor -1 and take the partial of the pressure at a constant temperature. So once we take the integral by using the Z factor of temperature with our interest, which was 20 degrees Celsius, subtracting by 1, dividing all of them by the pressures, and we obtained with our gathered values at table 4, I've shown here, we concluded that graph 3 shown in the table as well. So here we have our X and Y's and our temperature as well. So our pressure is at megapascal 0.5. We calculated our Y Gibbs energy to be -0.199 continuously all the way down, and our total area to be 6.58. And to conclude the calculation, and we graphed our data and to figure out the area under the curve. You can see how it's inclining, and then it hits that mark spot at 0, passing the 0, and it starts decreasing down. So this is our area under the curve for the residual Gibbs energy.
Residual enthalpy energy. To find enthalpy residual, so we can do HR is equal to H minus H ideal. However, because we do not have enthalpy for the ideal gas value, we must use the equation HR over RT is equal to the integral of P to 0, partial Z over partial T at constant P, which is shown below in table number 5. In table number 5 is calculated data for residual enthalpy energy, and it's from 0.5 to 1.4, and we get a total of -4.29. Then we constructed graph number 4, shown below for the data in table number 5, to see the curve and be able to calculate the areas under the curve. To find the area under the curve was determined again with the same step as in the Gibbs residual by using the formula of area for trapezoid with the points of reference of pressure from the range and used previously. Graph number 4 calculated data for residual enthalpy energy. So the graph is shown. And then for C is entropy residual value. And to find the residual entropy, all we have to do is subtract the residual Gibbs from residual enthalpy. And as shown in figure 1, we get our answer for entropy, -10.88.
And here is our discussion. So achieving our goals for the project, we found using the first and second law to identify, formulate, and solve was the best option for the completion of the project. We started with identifying our given variables and unknown variables, highlighting key points, understanding the problem statement, and finding informative information before making any calculation for the project to reach our expectation. Secondly, formulating was a major deal in this project. We needed to make sure every problem had a solution. With provided information, we applied knowledge and used resourceful equations like Gibbs residual, finding the reduced pressure and other equations throughout the objective. Last, solving was one of the crucial standpoints of the project. We needed to make sure every missing variable was found using mass balances, moles, and mass fractions, integration, and using coding calculations in Microsoft Excel. During our findings, we found that on our Z factor versus reduced pressure, the values dropped to nearly 0 for the reduced pressure and compressibility factor. In conclusion, even though we were very confused at the beginning of the project and did not know where to start and what to do, we have determined that Excel was the best program to use to find the property states for all the variables, such as temperature and pressure. We have determined this because of all the functions that are available with Excel that make finding calculations super easy and only make you do it once and just drag it across, and it applies by itself to the rest of the chart. Excel was also great for this project because it is very easy to make all graphs. All you need to do is highlight the data points that are going to be used and then just enter the variable names in units. It also helped us compare our actual gas to the ideal gas.
So just wanted to bring along with our actual Excel where we manipulated our data. So we were given our alpha team, we were given our specific conditions, which are critical pressure and temperature. So we had our actual data provided to us. And from there on, we had to create our ideal gas data. So within our chosen range of temperature, which we were given 20, and we decided to choose 20 to 120. So we took all those highlighted data, created them into a separate Excel here. And then once we did that, we calculated the ideal gas values for the volume residual. And we went down to the temperatures as well to calculate the Z vector for the volume ideal and the total. Once we did that, we went to reduced pressure and calculated the Z vectors from 1 till 11, our specific ranges. And then we graphed all of that. And this is how we actually got our data and our graph. And continuing on, we calculated our residual volume with our various pressures and figuring out our slope as well, our Gibbs energy, residual Gibbs, residual enthalpy, entropy, and calculating the graph to measure our area under the curve for the residuals as well. So this is our Excel that we did all our work in order to conclude with our report. Thank you very much.